In this screencast, we'll look at electrophilic aromatic substitution, specifically the synthesis of this molecule 4-iodo-3-nitrobenzoic acid. So one of the skills that you need to demonstrate in organic chemistry is the conversion of a given name to the structure, since organic chemistry is primarily a structure-based course. So we're going to use a specific way of converting this name into the formula. So we're going to use the main parent here, benzoic acid, and draw that first. So benzoic acid is the carboxylic acid of benzene. So benzenes are a six-membered ring here. So it's C6H6. So the substituent for the made parent is an acid, so that's CO2H. So that's benzoic acid, and that's going to take the 1 position, so we'll label that carbon 1. We go 2, 3, 4, 5, and 6 around the ring. And so everything else is a substituent. So the next thing we run into is 3-nitro, so we're at the 3 position. And nitro is, I'll draw out the Lewis structure for that, just so you know what the nitro group looks like. So the nitrogen actually bears a positive charge, and then we're going to show one of the oxygens bearing a negative charge. So there's plus, and then that's balanced out by the minus. And then finally we have 4-iodo. So at the 4 position we have the halogen. So that structure there corresponds to 4-iodo-3-nitrobenzoic acid. So the problem is to make this from either benzene or toluene and do subsequent EAS reactions. So one thing that we can look for in such problems like this is if there is a benzylic carbon, and we do have a benzylic carbon that's at oxidation state 3, it's at the acid. So it would be most appropriate to begin this synthesis with toluene, because that benzylic carbon can then be oxidized up to the carboxylic acid. So if we start with toluene, so methylbenzene, the common name of toluene, we can oxidize that benzylic carbon here up to the acid. And therefore, it saves us a step from starting with benzene where we have to install the methyl group. So at least we're starting with one of the substituents. So what we want to do now is consider this monosubstituted benzene, how the substituent methyl group that is on there, how it is going to direct the next substituent that goes onto the ring. So alkyl groups are electron donating through induction, so that means they are OrthoPara Directors. And what I'm going to do with this blue marker here is show you where the next substituent would go. So in the 1, 2, or 1, 2 the other way, so those are ortho positions, so ortho means 1, 2. And then if we keep counting, the 1, 4, that is the para position. So ortho is defined as 1, 2 relationship, and then para is defined as the 1, 4 relationship. So if we look at the relationship between the acid and the iodide, that is para. So we can generally assume that for an OrthoPara director, you're going to get more of the para isomer over the ortho based on steric hindrance. So with that knowledge, we can go ahead and perform our first reaction knowing that we're going to get substitution at the para position. We cannot, however, directly install iodine. So we have to do basically a functional group transformation to get to that iodine. So we're going to do a few steps here, the first of which is a nitration. So the first step, we're going to put the NO2 group on the ring at the 4 position. So the next question is obviously we need a nitro group at the 3 position and we need an iodine at the 4 position. So how does this help us? Well, we can use this nitrogen to our advantage. Right now, if we were to determine how the next substituent is going to go into the ring, this methyl group is still going to direct ortho. The nitro group is a meta-director, so it's going to direct or reinforce what the methyl group does. And so that really doesn't help us at all at this point. However, what we can do is reduce the oxidation state of that nitrogen down to the amine. So we can treat that with, say, iron metal in the presence of hydrochloric acid, and then do a basic workup where we're adjusting the pH so that the nitro group, which is reduced down to the amine, is isolated as the free base. So what we're doing now is reducing that nitro group down to the amino group. So the amino group is NH2. The nitrogen has a lone pair of electrons. And now if we consider the 2 groups, we know that the methyl group is still going to direct ortho to itself. The amino group is going to direct ortho to itself, but it's a stronger director through resonance. So the alkyl group is through induction, through the sigma bond. The nitrogen is actually donating through resonance, through the pi system. So it is going to win in terms of where the next substituent goes. So at this point, we can go ahead and do another nitration reaction. And what you'll notice is now that we have 2 differentially oxidized nitrogens. So we have an amino group, and then we'll have the nitro group. So we can use that to our advantage as well. So let's go ahead and do another nitration. So that is going to direct ortho to the amine. So here's our amino group, and the incoming group, nitro, goes there. So at this point, we have the correct substitution pattern of the ring that we're trying to make. Basically, what we need to do is some oxidation chemistry at the benzylic carbon. The nitro group is fine, and then a functional group transformation of the amine. So what we can do next, let's go ahead and transform this amino group to the iodide. And the way we're going to use that is through Sandemeyer chemistry. So we're going to form the arene diazonium salt using nitrous acid. So HONO is nitrous acid. So that's basically formed from taking sodium nitrite, NaNO2, plus hydrochloric acid will give you nitrous acid. That is going to transform the amino group into the arene diazonium, so which looks like the following. So you have N2, that's bearing a positive charge. And then in this case, we're going to have chlorine as the counter ion for the salt. So we have this arene diazonium chloride salt. And next, we're going to treat that with potassium iodide. So what that is actually doing is a nucleophilic substitution of N2. So you expel N2 gas and you substitute that for iodide. So where the diazonium was, we now get iodine. Our NO2 remains the same, and then our methyl group. So at this point, we are almost there. What's the last step we need to do? We need to oxidize this benzylic carbon, and the conditions for doing that are potassium permanganate under basic conditions, so say sodium hydroxide, water, and heat. So that's going to get you the carboxylate, which you then need to adjust the pH to acidic. We'll write hydronium ion to do that. And that does the last oxidation. So this has been a review of electrophilic aromatic substitution, so specifically the synthesis of 4-iodo-3-nitrobenzoic acid, in which we started with toluene. We installed a nitro group para to the methyl group. We then reduced the nitro to the amino, and that basically switched the directing group ability of the nitrogen. So now it's an OrthoPara Director, which we installed a new nitro group. So now we have differentially oxidized nitrogens. The amino group was transformed into arene diazonium, which was then displaced with iodide to install the halogen. And then finally, the benzylic methyl group was oxidized to the acid.